In this module, we will study a few functional forms that are used in regression models. Till now, we have said that we regress the variable y on a set of variables x. Now, we will see that this standard model, which is linear in parameters, can be modified in such a way as to include non-linear functional forms as well. In other words, we will convert non-linear equations in a format that makes them amenable to be used in the format of the multiple linear regression model. Let us begin with the linear logarithmic model. So, that is known in short as the lin-log model. So, we begin with the linear logarithmic regression model. An example is y is regressed on log of x2 and log of x3. So, the two regressors are log of x2 and log of x3. Obviously, this is not linear in x2, x3 and y, but it is linear in the parameters beta 1, beta 2 and beta 3. Question is, when do we use such a model and why are these models important? So, let us take an example. Supposing y represents the price of apartments, x2 represents area in square feet and x3 represents the number of bedrooms in the apartment. So, our model is basically price of the ith observation is equal to beta 1 plus beta 2 log of the square feet plus beta 3 log of the number of bedrooms plus ui. This model has an advantage over the model where we regress y on x2 and x3. The reason is, if we take any one variable, supposing we take only square feet, so we will be able to see that if there is an increase in the square feet measure, then the price increases, but it increases by smaller and smaller amounts. Let us see why. So, if we take the derivative del y del log x2, then we obtain beta 2. That means, beta 2 is the rate of change of y with respect to the rate of change of log x2, but this denominator can be further elaborated and we can write this del x2 by x2. That means, this is the percentage change in the square feet area, which really means that del y del x2 is equal to beta 2 divided by x2. So, if we draw a diagram showing y and x2, then the diagram would look like that. The slope of y with respect to x2 gradually decreases as the magnitude of x2 increases, assuming of course that beta 2 is positive. So, it means the incremental price due to increment in square root gradually decreases. The slope is not constant. So, the functional form is non-linear, but we can accommodate this functional form in the classical linear regression model, which is linear in the parameters. Let us now take a look at another example of lin-log models. Another example often used to explain linear logarithmic models is as follows. In cross-section budget studies, we often ask questions like the following. As people's income increase, what is the impact of their expenditure on food? So, we are trying to explain food expenditure, its movement with the level of income of the consumers. So, we write a model like food expenditure is regressed on the logarithm of total income of the ith observation plus the random disturbance term. As you would have noted, this is a simpler case. Earlier we had price regressed on two variables, square feet and number of bedrooms. So, here we have food expenditure regressed on the logarithm of total income. If total income is not available, then we can use total expenditure I. So, once again, if you plot food expenditure and total expenditure, you would get a relationship which is non-linear, and the slope of this curve gradually diminishes. However, the beauty of the classical linear regression model is that we can easily capture this with the help of the linear regression format, and this is called an Engel relation. So, Ernst Engel brought out the relation between income and various categories of expenditure. So, this is another widely used example to explain the concept of linear regression models. In both the cases, this one and the earlier one where we regressed price on the logarithm of square feet, in both these examples, the variables are, this is y, this itself now is a variable x, this is another variable x. So, y is regressed on say x2 star, which is logarithm of square feet, and x3 star, which is logarithm of bedrooms. And the same procedures, same estimation procedures, same procedures giving rise to the sampling distributions, they once again hold good because of the classical properties, the properties of the UI, which is basically independent normal with mean 0 and variance sigma square, and independent obviously means there is no correlation, and also there must be no multi-collinearity between the variables. So, that is another example of the linear logarithmic models, and we get the estimates, we find out the standard errors, we find out the t values, then we test whether the estimates are statistically significant, and we proceed to make future projections or predictions. Now, let us take a look at another class of nonlinear equations known as the log-log model or double log model. In economics, we often use a concept called the production function. So, the production function basically shows output as a function of inputs. Let us say output is Y and there are two inputs, labor and capital. So, Y is produced with the help of labor and capital. How do we write this? An often used production function is given as yi is equal to a ki to the power alpha li to the power beta exponential ui. You will have noted that I is the observation which runs from 1 to n. So, I runs from 1 to up to n. So, yi is the ith observation on the output, corresponding to which capital input is ki and labor input is li, and each of these has powers. So, ki to the power alpha, li to the power beta. Now, obviously once again this is a non-linear relationship, but we want to use the classical linear regression model and estimate this relationship. So, what we do is we take the natural logarithm of this equation, both sides of the equation. So, what we get is log yi is equal to log of a plus alpha log of ki plus beta log of li plus ui. So, that once again is a standard classical linear regression model. So, in other words, we can write this as yi star is equal to beta 1 star plus beta 2 star x 2I plus beta 3 star x 3I plus ui. So, what we have done is we have denoted log of a by beta 1 star, alpha as beta 2 star, log of ki as x2 and log of li as x3, while beta is denoted as beta 3 star. So, this format suits the classical linear regression model. Now, as earlier, we estimate this model by regressing y star on x2 and x3, or sometimes they say y star on x2 star and x3 star. These are just matters of notation. So, the variable is no longer ki, it is logarithm of ki, that is denoted as either x2i or x2i star. Similarly, logarithm of li denoted as x3i or x3i star, and accordingly we run the ordinary least square estimates. These are obtained. question is, like the earlier case of linear logarithm models, how do we interpret this regression? So, coming back to the original form, we see that the partial derivative of log y with respect to log k is alpha, which is actually defined as beta 2 star. So, this partial derivative has a very special significance in economics. If you evaluate the left hand side, del log k of log y, this is equal to del y by y divide del k by k. And if you multiply the numerator and the denominator each by 100, then the numerator and the denominator, the ratio is percentage change in output divided by percentage change in input. So, this is basically the percentage change in output arising out of 1% change in capital input, and this has a very special significance. It is called elasticity. It is called the elasticity of y with respect to k. Similarly, del log y del log L, which is beta, or here defined as beta 3 star, this is equal to the ratio of percentage change in output to percentage change in labor input, and that is defined as elasticity of output y with respect to labor. Obviously, since alpha and beta, that is beta 2 star and beta 3 star, since these are parameters, this model is also known as the constant elasticity model. It is also known as the constant elasticity model. Just to refresh what we have studied, so once we have estimated this model, we can test H naught whether beta 2 star plus beta 3 star is equal to 1 against H1 beta 2 star plus beta 3 star not equal to 1. So, if you go back to the earlier models where we studied testing of hypothesis, you will note that having estimated this model, we carry out tests of hypothesis. For example, here beta 2 star plus beta 3 star equal to 1 means elasticity with respect to k plus elasticity with respect to L is equal to 1, which means that if you increase k and L by the same proportion, say by 2% each, then output would also increase by 2%. This is widely known as constant returns to scale, and the alternative hypothesis is that beta 2 star plus beta 3 star is not equal to 1. That means we are challenging whether there is constant returns to scale. So, we can measure the sensitivity of output with respect to the inputs, and all the standard techniques, tools and procedures that we have studied in case of testing of hypothesis, they follow once again in line, because this model has a UI disturbance term which follows the properties of the classical linear regression model. The next example that we will take is log lin, that means logarithm on the left hand side and linear on the right hand side. So, now we take a look at log lin models, that means models where log y, or in natural logarithms it is ln y, is regressed on variable x2 plus u. So, we might ask the question, what is the use of this model? Till now, whatever we have studied, the different types of regressions, they were basically cross-section regressions, data using cross-section. This is one particular case where we will briefly touch on data using time series, very elementary application of time series. So, if we plot time continuous on the horizontal axis and log of y on the vertical axis, and if we get a relation which is linear, then the slope of this is equal to the rate of growth of y. So, viewers, you might have guessed that this kind of model is used to estimate growth rate, linear trend in growth. That means, if we write log y is equal to beta 1 plus beta 2 t, please note x2I has been replaced by t, and so to maintain symmetry we are replacing that I by t plus ut, where say t runs from 1 to up to n, or some texts will say t runs from 1 to capital T. So, this is a model where log of y is regressed on time, and time is continuous here. So, here if you take the derivative of the left hand side, that is log y with respect to t, then we get del log y, or del t of log y is equal to beta 2. But the left hand side is nothing but del y by y divide del t, that is, this is del, not del y by y divide del t, but it is del t of y divided by y. So, del t of y divided by y. So, what is the numerator? It is the rate of change of y with respect to time, and what is the denominator? The value of y. So, with 1 unit of time, this numerator shows with 1 unit of time how much y increases, and the denominator shows the value of y. So, this is nothing but the rate of growth of y. Typically, if y is the national product, gross national product or gross domestic product, then we can use this kind of a regression to find out the trend growth rate. So, what is the growth rate here? It is beta 2. So, the estimated model will be log y t hat estimated as beta 1 hat plus beta 2 hat t plus u t. So, this estimate will be obtained as the slope of this fitted line, and that is given as beta 2 hat. So, if this is the estimated line, it is beta 2 hat, or if it were the population regression line, it would have been the parameter beta 2. So, from here what we note is that this is the rate of growth, but it is the continuous rate of growth. It is actually the continuous rate of growth. So, if we want the discrete rate of growth, we can make a simple calculation and go back to the discrete rate of growth. So, let us consider the model where we write y t is equal to y0 into 1 plus g to the power t. So, that is nothing but our familiar compound interest formula. Y t is original y into 1 plus growth rate. This is the discrete growth rate over how many time periods? T time periods. So, we can write log y t is equal to log y0 plus t times log 1 plus g, but that is a deterministic relation. So, what we do? We add ut, and that is exactly our model what we had written, beta 1 plus beta 2 times t plus ut. But note here that beta 2 is log of 1 plus g. So, what we obtain as beta 2 hat, so beta 2 hat is nothing but 1 plus g hat. And since we have taken natural logarithms, what we can say is g hat, or the estimated discrete growth rate, is equal to exponential beta 2 hat minus 1. So, because this is log of, this is log. So, because this is beta 2 hat is the estimate of log of 1 plus g, it is the estimate of log of 1 plus g. So, you raise beta 2 to the exponential e, consider exponential e beta 2 and subtract 1, that gives us the discrete growth rate g hat. So, from the model, from the regression model, we obtain the continuous growth rate, and then we can move backwards and we can calculate the discrete growth rate. So, these are three basic nonlinear forms that we have studied in this module, namely the linear logarithmic model, lin log, the double model, double log model, log log model, and finally the log linear model, which is used as a simple model to estimate the growth rate or the trend. In the next module, we will look at some further functional forms. In the meantime, please go through the study materials where these examples are given and numerical estimates are shown with their t values, with their standard errors, with the r squares, so that you can get a feel of how these models are estimated.